Dulcis in fundo, we have Vladimiro Benedetti from Université de Bourgogne-Franche-Comté. He will talk about divisors in the modular space of the Barvoisin varieties.
Thank you. And first of all, I would like to thank the organizers for inviting me here. It's a real pleasure to be here in this nice conference. So I will talk about the Barvoisin varieties, which are hyperkähler varieties, and some results concerning their some divisors in the modular space of these varieties. But actually, the goal of my talk is to explain to you that there is a connection between some Fano varieties of K3 type. I will not define K3 type, but let's just say some Fano varieties and some hyperkähler varieties. So I will just recall the definition. A Fano variety is a variety with anti-canonical bundle ample. And these varieties have nice properties, boundedness properties. So for example, for each fixed dimension, you have finite number of deformation families. So you can classify them. And Fano varieties have, let's say, negative canonical bundle. And hyperkähler varieties are varieties which have trivial canonical bundle. So there is quite a big difference between the two. Hyperkähler varieties are quite important because, so by Bogomolov decomposition theorem, when you have a Kähler manifold with trivial canonical bundle, modulo et al. Cover, you will get a product of these three types of varieties. So complex tori, which are more or less understood, strict Calabi-Yau, which I will not define, and hyperkähler varieties. And the definition I will take for this talk is the following one. So hyperkähler variety is a compact Kähler simply connected manifold with trivial canonical bundle, and such that there exists a unique up to scalar holomorphic symplectic form. So the existence of this form explains why sometimes they're called irreducible holomorphic symplectic varieties. And in dimension 2, they're also called K3 surfaces. So let me just say that in dimension 2, there is only one deformation family of K3 surfaces. So there are some issues with hyperkähler varieties. The first one is the fact that there are only few known deformation families, which are listed here. So, for example, the first example is you take a K3 surface, so a hyperkähler variety of dimension 2, and then you construct Hilb n of S, which is the Hilbert scheme of n points on the K3 surface. And then you deform it. So a hyperkähler variety of type Hilbert S is a deformation of a Hilbert scheme of n points on a K3 surface. So here, just bear in mind that, let's say you have the moduli space of hyperkähler varieties. Let's say that in the following of the talk, they will all be polarized. So I will assume from now that they are polarized. The moduli space of polarized hyperkähler varieties with a fixed polarization. And inside of this moduli space, you will have countably many divisors, which, okay? And on these divisors, the hyperkähler will be isomorphic to a Hilbert scheme of n points on a K3 surface. But the very general hyperkähler variety will not be. And it would be interesting to understand what this kind of varieties here we have. So I will come back to this picture later on. So the second example is constructed, let's say, more or less similarly from a two-dimensional tori. This is the generalized Kummer construction. And then so the first two examples were constructed by Beauville. And then there are two exceptional cases constructed by O'Grady. So the first problem is that there are few known deformation families, and the second problem is that there are few known maximal dimensional explicit families. Otherwise stated, I mean, there are few families in which we know the very general element, deformation, which is a deformation of the Hilbert scheme of endpoints on a K3 surface. And these are given, so these are some examples. We have some moduli spaces on cubic fourfolds, Gushel-Mukai varieties, and the Barvoisin varieties. So, and I will talk about the Barvoisin varieties. So one remark is that in all these examples, in these families, the hypercolor variety is associated with a Fano variety. So for example, for instance, in the case of modular spaces on cubic fourfolds, the modular spaces are hypercolor, and the cubic fourfolds are the Fano varieties. One can associate to them. And the relation is quite precise. It's on a Hodge theoretical level, but also on a derived categorical level and a birational level. And maybe I will say some things about the birational point of view. Okay, so I will define the Bar-Voisin varieties. So one just take a sigma, which is a 3-vector in 10 variables, 3-form, let's say. And so one can see sigma as a section of this bundle, which is wedge 3, so the third skew-symmetric power of U dual, where U is the tautological bundle of rank 6 on the Grassmannian 610. So the Grassmannian of 6-dimensional subspaces of C10. So sigma defines a section of this bundle, and one just takes the zero locus of the sigma, and this is, by work by Debar and Voisin, a hypercolor fourfold, which is, for generic sigma, a deformation of a Hilbert scheme of 2 points on a K3 surface. And then there is the Fano side. So there are many Fanos that one can define. I just chose to present 2 of them. So sigma is a 3-form. Okay, so it defines a hyperplane in the projectivized of wedge 3 of C10. So it defines a hyperplane section of the Grassmannian 310 embedded via the Plucker embedding. Okay, so there is this H, which is a hyperplane section of the Grassmannian. And then there is this P, which is the so-called Peskin variety, or 6-fold. So you take any element in P of C10. It is associated to a vector X. Then you have a vector. You have your sigma, which is a 3-form. You contract them. You obtain a skew-symmetric matrix, a 2-form. And so you define P as the set of such points X, where the rank of this matrix is at most 6. And these 3 varieties are all constructed from sigma. So you see that there is a family of these varieties parameterized by this GIT quotient of the space of 3 forms, modulo linear equivalences. And this is a maximal dimensional family. So the picture of M here is, let's say, this space, birational to this space by a result by O'Grady. And so the idea now is to study some divisors in this modular space. So divisors in M, so one can construct them in different ways, but one way, if one wants some explicit divisors, one idea is to construct GL10 invariant divisors in the space of 3 vectors. So the first divisor was studied by Debar and Voisin already in their first article about the Bar-Voisin varieties. And it's the divisor of sigmas where the hyperplane section is singular. And one can show that the hypercolor variety is singular as well. And it's singular along a K3 surface. And Y is birational to the Hilbert scheme of 2 points on this K3 surface. So in the picture, this divisor would be rather a boundary divisor because Y is not smooth. So let's say it's something like this. Okay, and Debar and Voisin used this divisor to show that Y is a deformation of Hilbert of S. Okay, then there is another divisor, which I will not talk too much, which is dP. So it's defined the following way. So sigma such that Y contains a plane. And using this divisor, since one has a plane in Y, one has some extra cohomological class, one can prove some very precise Hodge theoretic results relating Y, H, and P. So this was done by Debar and Voisin, and then by myself and Jiao Song. And then there is a third divisor, which we studied with together with the Jiao song, which is defined in this way. So you take the 3 vectors for which there exists a point in P of C10, such that the rank of the matrix I explained to you how to construct before has rank at most 4. Okay? So this will be a singular point of the Peskin variety, if you want. And we show that if sigma is general in this divisor, then Y, so the hypercalar, is a moduli space of twisted sheaves on a K3 surface. So I will not explain this, but the precise statement is that there exists a Mukai vector and there exists a Brouwer class on the K3 surface, on a certain K3 surface, such that moduli space of sheaves, of twisted sheaves on the K3 surface is isomorphic to this Y. Okay, so if you want, this divisor is, let's say, something which in general is not isomorphic to IBAN of S, but will intersect some of these other divisors. So this is dr. Okay, so now I will pass to the birational point of view. And I just recall that there is a conjecture by Asset, and then it was translated by Addington, that says that a cubic fourfold is rational if and only if the associated hypercalar variety is birational to a moduli space of stable sheaves on a K3 surface. So these moduli spaces of stable sheaves on a K3 surface, they are deformation of, again, N of S. And so will appear here in the picture as well. There will be more divisors like this. And the conjecture, okay, this is the moduli space of the Bach-Voisin varieties, but the same picture holds for cubic fourfolds. And the conjecture is that a cubic fourfold should be rational exactly when we are in these divisors. Yeah. So one can ask the same question about the Bach-Voisin varieties. So when Y is birational to a moduli space of stable sheaves on a K3 surface, is the Peskin variety or the hyperplane section rational, for example? And so, of course, in this case, we just have 2 divisors for the moment. It would be nice to construct more divisors. So one can try to answer this question on these 2 divisors. And so with Daniele Faenzi, we proved that if sigma is general in this boundary component, okay, remember that here the hypercalar is birational to the Hilbert scheme of 2 points on a K3 surface. Then the Peskin is rational. And okay, the proof is not trivial, even though it seems trivial. But you do what you expect. So the Peskin variety is singular along a P2, and you project from the P2 to a P6, and the restriction of this projection to P is birational. And there is some work in progress for the Peskin varieties contained in this divisor, ds. So we have some cohomological condition which ensures the rationality of the Peskin variety. And now we would like to compare this condition with the condition that the twisting of the moduli space here in this theorem is trivial. Okay? Because the twisting is trivial exactly at these intersection points where the hypercalar variety is birational to a moduli space of K3, of sheaves on a K3 surface. So yeah, here are some questions. So we would like to understand the rationality of P on the divisor dr, yeah. There is a question to translate the rationality conjecture in the right categorical terms, which has been done for cubics. So the question is, can we do it for the Bach-Voisin varieties? And then there is a question if we can construct more divisors in this moduli space. Thank you.